All right, so now we'll talk about the data structure of a heap. And it's a way of structuring data, and we can use, there's applications to this. One of the biggest applications is the sorting algorithm HeapSort. So first we'll just talk about what is a heap. So a heap, have you guys heard the word heap? It's used in English, not in computer science, but ends up being, you know, a big pile, or maybe you've seen you take a heaping teaspoon or something. So anyway, it ends up being, yeah, like a big pile, maybe a disorganized pile. So this is the definition in the dictionary of what a heap is. And then in computer science, we use the word heap basically to mean a collection of data items that are organized kind of in a disorganized pile, but not completely disorganized. It's not like there's no rhyme or reason to their connection to each other. They will have a connection to each other, and the connection is that either the biggest element or the smallest element will rise to the top. So in that sense, it's one of the many examples of a priority queue. A priority queue is a data structure where you put items into it, and then the items get taken out, not in a first come, first serve method like a regular queue, but they actually come out based on the one with the highest priority, or maybe the lowest priority, comes out first. So a heap is an example of a priority queue. And an example of a heap would be a structure like this. So for example, this would be what's called a max heap. So the maximum numbers are considered the ones with the highest priorities. So in this case, we have 100 at the root. This is now a tree. So if you remember in computer science, a tree is any graphical structure that has no cycle in it. So this is a tree. Happens to be a binary tree because every node has exactly 2 children as it's coming down. So we could call this a binary tree. And then it's also considered a max heap because for every node, if the value of the node is greater than or equal to its 2 children, then that node is considered to be following the heap state. And if that's true for every node, then the entire structure is a heap. So, for example, 100 is greater than 19 and greater than 36. So therefore, this node 100 and these 2 children node are correctly in a max heap. 19 is greater than 17, and it's also greater than 3. So these 3 nodes are in a max heap layout. 36 is greater than 25 and 1, so this is legitimate max heap. And 2 and 7 are both less than 17. So this entire structure is a heap, a max heap. The fact that 19 is less than 25, and 19 is at, let's say this is level 0, and level 1, and level 2, and level 3. 19 can still be greater, can be less than 25, and that's okay. That's an important concept to know. So this is still considered a heap. Even in the event that 19 is less than 25. Okay. Okay. What we could do, we could use the data structure of an array to represent a heap. For example, we can decide to let, this is an array of numbers, and we take these numbers and put them in this arrangement, and then we could just declare, like in our mind, this is a heap. And what that means is that the first node is node 0. This is node 0. It has 2 children, node 1 and node 2. Here's node 1 and here's node 2. And then node 1 has 2 children, which is node 1, which is 19, has 2 children. These 2, 3 and 4. So the values are 17 and 3. Right? And node 2 has 2 children, which are 5 and 6. And then node 3 has 2 children, which is 7 and 8. So if you wanted to know the relationship, so this is now a binary heap. You wanted to know the relationship between the parents and children. The relationship is like this. Node I has the parent, you take your value of I, you can subtract 1 from it and divide by 2, and then take that result and round down. So for example, and that's this little awkwardness with the -1 and the divide by 2 is because in computer science we always start arrays with the index of 0. So for example, if you wanted to know who the parent of, let's say, number 8 is, we would take the index 8, we would subtract 1 to get 7, divide that by 2 gets us 3.5, and then we round that down and the parent is 3. A little bit of an awkward algorithm to figure out who the parent is. And then if you're a parent and you want to figure out who your children are, you can do pretty much the reverse operation. So if you are node J, come on in. If your node J has the 2 children, J times 2 plus 1 and J times 2 plus 2. So the 2 children of number 3 would be 6 plus 1, which is 7, and 6 plus 2, which is 8. So you can figure out who your parents are, you can figure out who the children are. Okay, so now if we want to now look at the structure and we want to do maybe some operations on it. So for example, suppose we wanted to insert a new number into the structure. Let's say we wanted to add number 9 here, index 9, and let's say the value we're putting in is, it'll make it go all the way up to the top, we'll say 200. We're trying to put in a 200. So what we could do is we could add a new number, we put a 9 here, right, 200. So that'll put 200 will be a child of 3. But now the 3 and the 200 are not following the heap property. So how can we get this new value? So here's what we're doing. We have a heap, and now we have a brand new value, but we don't know where it belongs. So we can kind of slap it on the end, but then it's not really a heap. How can we get this to turn back into a heap again? If we have, so the question is, given a heap and a number, how do you put the number into the heap so that the new structure is now a new heap? Right, so take the new number, which would be, let's say, 200, compare it to 3, and if it's less than 3, now if it's greater than 3, because this is a max heap, we would swap it. So then the 3 would become the child of the 200. And then are we done? If there was a 200 here with a 3 as a child, are we done? No, because we have to check, is 200 less than its now new parent, 19? And if so, we would swap those values. And now 200 would be here, and 19 would be here, and 3 would be a child of 19. And we have to keep doing this until we get to the point where there's no more swapping. And when there's no more swapping, then we're done. So in that case, 200 would swap with 100, and 200 would be here. 100 would be here, 19 would be here, and 3 would be a child. And it's very important, how many operations would that be? So we're in a binary tree. We're starting at the bottom, and every time we do one of those compare and possibly swap, we hop up a level. Then we do another one, we hop up another level, and we hop up another level. We don't always have to go to the top, but we have to go to some height and then we stop. So it's proportional to the height of the tree. But what is the height of a tree? If a tree has, a binary tree, has n levels to it, I'm sorry, if it has n nodes to it, what is the height of a binary tree? That would be log n. Actually, it would be log base 2n. And then the idea is, so the running time of an insert operation would be log n. So if you had a heap and then wanted to put a new number into it, that would be an operation of log n to get that done. So if you had n numbers that were random and you wanted to put them all into a heap, you can start with the first one, or maybe the second one, and consider the first one already in a heap, and then add the second one to the already existing heap. Then add the third one to the already existing heap. Then add the fourth one to the already existing heap. So that would be a log n times n number. So you can take random numbers, turn them into a heap by running an algorithm that runs n times log n. For each number inserted into its correct spot. Okay. And by the way, if we wanted to delete a number, this might be later on down the road, if we wanted to delete a number, let's say we wanted to, so we would have to somehow have some kind of a side index, a data structure that says, you know, the number 19 is right here. So suppose we decided we want to delete the 19. Okay, so we want to get rid of the 19. So if this was an empty value, that's no good. So how can we then turn this back into a heap? So this would be a question where, given a heap and a particular number you want to delete, how would you do that? But you'd have to somehow be able to get access. This will be for algorithms we'll do later on in the course. But if we had a particular number we wanted to get rid of, we can say, okay, let's erase this number, but now what do we have to do with the children? Compare the two children, whichever one is bigger gets a promotion. Now we have nothing here, and then we'd have to say, okay, out of the 2 and the 7, 7 goes up here. Okay, and how long does that take? Well, we're going to start at a certain level, and then we're going to just walk down the tree until we're done, until we hit the bottom. So again, that would be a log n operation. Deleting from a heap takes log n. Inserting into a heap takes log n. And, okay, now the other thing is we don't have to use, a heap doesn't have to be binary. A heap could have multiple, you know, each node could have many children if it wanted to. And actually, the more children it had, the shorter the tree would be. So it would be not log base 2, it would be log base 3 or 4, however many children there are, to get those operations done. In order to do that, in order to not use an array as our structure, we'd have to use references in Java. So for example, we can have data, maybe our data is an integer. And then we can start having references to nodes. So we create a structure called a heap node. So we're using classes in Java to create a structure. And it has data. And then maybe, it's up to you, you could have a reference to its parent. You could have a reference to its left child, its right child. So a binary tree would have left and right children. You could also have an array of children if you want to have many children. Or you could also just, you know, not reference the children, just every node points to its parents. Then you can only walk up the tree, you can't come down the tree. But yeah, so there's no requirement that a heap is binary. It's just if you use an array, it becomes very easy to do. Okay, so some operations we can do on a heap would be delete the maximum number or delete the minimum number if it's a max heap or a min heap. We can increase a key. We can take a value and increase its value. If we increase it, we have to then compare it to its parents to make sure it gets into its correct spot. And we can insert a new value into a heap just by putting it at the very bottom and have it walk all the way up to the top to its correct spot. We could also, this is easy to do if you don't have a binary tree, we could merge two trees together. So if you wanted to take two trees together, two heaps, you wanted to put two heaps together. Suppose, for example, we had this heap, let's say we had this heap, and then a sister heap, and we wanted to put the two into one big heap. What would we have to do? If you wanted to take two heaps and merge them into one big heap, you would take the root of one and the root of the other and ask which one's the biggest one, and that becomes the new root. And let's say there was a sister heap and 100 was bigger than it, so 100 went up to the top. Now we have a missing spot here, and we take these two and promote this one up. 36 would go here, and 25 would go here, and now we've merged the trees together. So merging, I keep calling them trees, merging the heaps together. So we can merge heaps together, and that's a pretty easy thing to do too. Okay. So then there's an algorithm called HeapSort. Now that we're good at using heaps, what we could basically do, since we can create heaps and delete members from heaps and turn it back into a heap, if we could take this collection of random numbers and step one, turn it into a heap like this, we could now create the sorted version of this array by popping or taking the top number out and putting that at the end of our answer array, and then turning the structure back into a heap, comparing 36 to 19 and put the 36 here, compare 25 and 1 and put the 25 here, and now we have a heap again. Then we pop out the 36 and turn it back into a heap. So we pop out the top number and turn it back into a heap, and just keep doing that until the heap goes away. And then we have all our values sorted. So probably the biggest application of heaps is a sorting algorithm called HeapSort. And HeapSort has 3 parts to it. So there's a heapify routine, a method for Java programmers, functions for C and C++ programmers. So heapify takes an array and an index, and it traverses down the binary heap and inserts the passed-in index into its correct spot. So build heap will call heapify to insert every member into the heap. So step 1, we're going to build the heap. Step 2, we're going to take the heap and build a sorted array by popping the top and then calling heapify again. And each time we pop the top, we take the value at the top of the heap and put it at the very end of our sorted array. So the kind of pseudocode for the heapify routine, you take an array and a certain index, and you're comparing the left and right child, and if the left and right child beats the parent, then you do a swap, and then you work your way up to the top of the heap. So for example, heapify, let me go back to our heap. The way the algorithm would work, suppose this wasn't a heap, suppose this was just a collection of random numbers. What we're going to do is we're not going to call heapify on the bottom leaves. We're going to call heapify on any node that has children. And what we'll do is we'll say, out of these 3 nodes, let's put the top number here. Then call heapify, so we're just going to work from starting from here and then going backwards all the way to the top. So we take these 3 nodes, turn them into a 3-node heap. Then take these 3 nodes, turn it into a 3-node heap. Then take these 3 nodes, turn it into a 3-node heap. Now with these 2 in their correct spot, we can take these 3 nodes and put it into a heap. And so on. So that's the way that algorithm works. So heapify does those steps. Takes the 3 nodes, turns them into a heap, and then walks its way up, walks its way back down to the bottom of the tree. So to build the heap, we're gonna call a method called build heap, which will say from I equal, this is an equal sign. I don't know why Linux turns these equal signs into like S's, but from I equals the length of the tree divided by 2, all the way down to 1. So basically we're gonna take, it's basically all the indices that have children, and we're gonna call heapify on those. And that's how we're gonna build our heap. Then once we've built our heap, this is the routine that will take a set of random numbers and turn them into a legitimate heap. So HeapSort will do step 1, build a heap, and then for I equals the length of the array down to 2, we swap the values. We take the value of the end one and the first one, we swap them, and we reduce the size of the heap by 1. So basically they're actually taking the index and copying it into location 1 of the array. And then they're calling heapify again. So really this is the routine where we are popping the value at the end of the heap and putting it at the end of the array. So there's 2 steps to heap sorting. Heapify, each step takes log n. And when we're building the heap, we call that n minus 2 times. So pretty much for every node that has children, which is half the nodes will have children. So that's proportional to, n divided by 2 is proportional to n. If you double n, you're going to double the number of times you have to call this routine. So that's really has a running time of n log n to build the heap. It takes n log n. So then HeapSort calls build heap, which is 1 step that takes n log n. And then it calls a separate step where for every node that's at the top of the heap, pops it out and puts it into its sorted order. And then has to rebuild the heap again every time it pops one out. So for every number, n, it's going to rebuild the heap, which takes log n, to rebuild the heap after you've deleted something from the heap. Okay, so since HeapSort has two separate steps, each one taking time proportional to n log n, and you have to do both steps separately, the overall algorithm is n log n. So that's basically saying if we were to double the input, our running time would be double plus log of one extra unit, so a little bit more than double the time to run HeapSort. Okay, and an application of a heap, not HeapSort, but just one side application of a heap, is a pretty famous problem in computer science called the building silhouette problem. So this is when software tries to take like a skyline, and then if you're trying to do a computer generated like flying around the skyline, from different points of view, you have buildings and you're trying to see what would it look like from your point of view. So the way this question works, it's a popular question that Google asks on job interviews. It's a very popular Google question. And the question goes like this: if you were given a series of inputs, and the inputs are buildings, and you're giving like building one has the left part of the building is at location 3, so we have an x-axis going across. And the right part of the building is at location 7, and the height of the building is 4. And then you have a second building. Yeah, I'm sorry these stars didn't come out. they got changed a little bit from the PowerPoint going on Linux. But anyway, so the idea was, I mean, you get the idea. So starting at 11, we have a building, and all the buildings are just rectangles. There's no fancy roofs or anything like that. All the buildings are just rectangles. And it starts at location 11, it ends at location 20, and its height is 8. And then there's a third building that starts at 15, and it goes all the way to 29, and its height is 3. So what you have to do is draw the building skyline without the overlapping buildings. So basically you wouldn't draw this part. You would just draw this part and this part. You draw that, you'd leave out the stuff that's in red. So the question is, can you come up with an algorithm to do this? And if you're just thinking off the top of your head, what would you have to do? So you can go, there's no rule that says the inputs are sorted from left to right. The inputs could be random. And you want to know at all points in time, what is the tallest building of all the buildings I'm currently considering? So, what could be an algorithm for doing that? So one thing we could do is we could take all our buildings and sort them. So all the buildings have 3 attributes, a left, a right, and a height. We can sort them based on their left field. So now we have the idea of we can walk across from left to right and look at all the buildings in our input from left to right. Every time we see a new building come in, we add that height to some structure. And every time we hit the end of a building, we delete that building from some structure. And also, at all times, we need the structure to tell us of all the items in the structure, which is the current tallest building. Because all we're doing at all points in time is printing the height of the tallest building. So, for example, when this second building enters into our data structure, it's our only building, but when we hit here, we add in a third building, but it's not as tall as this one, so we can't ignore it because it's going to later on become the tallest building, but right now it's not. So we have a structure that says we have this, and the tallest one is this one, but we want to keep this one around because it may become the tallest one a little later on. And then when this one eventually gets deleted, this would then rise to the top of our structure and say this is our new tallest building. So we'd have to think of a structure, think of all the data structures we have that have the probability, that have the that have, by its nature, can tell us what's the tallest out of all of them. And we're gonna be doing a lot of adding and deleting of buildings. We don't want that to take up a lot of time. So a heap is a structure that can always tell us what's the tallest one out of all of them. And deleting and adding, as we said, takes log n times. What is n? N is gonna be the number of buildings. So hopefully, this city doesn't have a lot of buildings, but adding a new building will take log, let's say the number of inputs, b is the number of buildings. So it'll take log b to add a building, log b to delete a building, and constantly spitting out the highest one is a constant time operation. You're just reading the top of the heap. So, solving the problem that way, how many operations would we have to do where we add a building? So you're given a problem that has b buildings, and let's say the city goes from 0 to n in integer values. So how many times will we have to add a building before we're done with our algebra? Add a building to our heap. We'd have to, there's b buildings, so we'd have to add, every building gets added once and every building gets deleted once. So that would happen b times. And in the worst case scenario, all b buildings will be in there, so it'll be b log b for adds, plus b log b for deletes. And then for all n steps, we're just printing out the top value of the heap. So it'd be b log b plus b log b plus n. N being the x-axis of the city would be the running algorithm for that. So that's just, an example besides sorting, an example of how we could use heaps. Okay, so a heap is a data structure that by its nature, taking a bunch of random numbers, it'll take n log n just to turn it into a heap. But once you have a heap, adding something new takes log n, deleting something from it takes log n. And it has the side property that at all points in time, it'll always tell you what the biggest or smallest item is in it at constant time. It'll tell you at all times. So it is a priority queue too.